Example 6.5. The background of this example is that the tangent plane to a surface at a point, as we've defined it, has the same slope as the surface in the x and y directions. But what about the other directions? If you start at a point and move in any direction along the tangent plane, is the slope of the tangent plane in any direction the same as the slope of the surface? We imagine it to be so, but that's because we typically imagine smooth surfaces, and the point of this example is to show that it's possible to have surfaces where the tangent plane at a point does not have the same direction as the surface, the same slope as the surface in any direction. So let's find the tangent plane to this surface here. It's given by this equation, z equals x to the 1/3 times y to the 2/3. Now, it's always good to try to visualize something or plot something. I'm going to show the plot a little later. I don't want to show it now. Now, we want to find a tangent plane. If we go about using the formula for a tangent plane and try to take some partial derivatives, we'll find something funny happens. And indeed, that's the whole point of this exercise, is that something funny happens. So let's just not do the partial derivatives just yet. I'll explore that a little later. Right now, we just want to work with the definition of a tangent plane as having the same slope as the surface in the x and y directions. So let's find the slope in the x direction at the point 0, 0, 0. Well, here's the key observation, is that along the x-axis, and what's the definition of the x-axis? It's when y is equal to 0. The function, z, the value of z given by the function is simply x to the 1/3 times 0 to the 2/3, 0. So along the whole x-axis, z is 0. Okay? So that means the slope in the x direction is 0. Z is not changing along the x-axis, it's always 0. And similarly, by a similar reasoning, you can say that the slope in the y direction is 0. If you plug in x equal to 0 into that equation, you'll of course get 0. So z is not changing along the y direction either. It's 0 along both axes. So the equation of the tangent plane is really simple then. Tangent plane at the origin 0, 0, 0. It's just z equals 0. It's that simple. So there's the tangent plane using the definition that the tangent plane has the same slope as the surface in the x and y directions. But something seems funny about this, because it's clear that z is changing with x and y. When you look at the function here, z equals x to the 1/3, y to the 2/3, as you move away from the origin, this is going to change. This value is going to change. So, in particular, but we've seen that if you move away from the origin in the x direction or the y direction, z doesn't change. But certainly if you move in other directions, this has got to change. So let's consider, let's now consider, let's start at the origin in the xy plane, xy equals 0, 0, and let's move in the direction 1, 1. So we can parameterize this line by x equals t, y equals t. And then along this line, z, let's just plug in the value for x, it's t to the 1/3. And then the y is also t to the 2/3. So this is t to the 1/3 plus 2/3 is t. So along that line, z has the value t. So the slope along this line is found by differentiating z and evaluating t equals 0, which gives the origin. Whoops, 1. The slope is 1. So if you move in a different direction away from the origin, you get a different slope. Now what's going on here? What's going on? Well, it's essentially this, that if you take the partial derivative of z with respect to x, let's say, differentiate with respect to x, you get a 1/3 coming down, x to the minus 2/3, y to the 2/3. Okay. And if you plug in xy equal to 0 here, you'll get something that's undefined. This is undefined at 0, 0. In fact, it's undefined whenever x is equal to 0, so in particular at the origin. And that's really the reason behind the wackiness here, is that the partial derivatives of this function are not defined at the origin. And so we're not allowed to use that formula for the tangent plane that uses the partial derivatives, because the partial derivatives aren't defined. Now let me show you a picture of what this function looks like. So I just used Wolfram alpha to draw this. So here we go. Let me slide this in here. There's a picture. So there's Wolfram alpha. Here I plotted this function here, and then here's what you get. So it looks like a square piece of paper, and it's been pinched along the positive x-axis. It's been pinched up. Along the negative x-axis, it's been pinched down, and then along the y-axis here, it has this infinite slope. So things are really kind of wacky at the origin here, and the tangent plane that you get by taking the slopes in the x and y directions will just be z equals 0, but it's clear that if you move in other directions, you will in fact, the value of z will change, and so the slope as you move in the direction, in particular 1, 1, the slope is 1 as we've seen, not 0. Now, as long as the partial derivatives exist at a point, which they don't for this example, but if they do, then we can use the tangent plane formula and we don't get anything wacky like this appearing. But this is a neat example in the sorts of things that can happen with non-smooth functions.